All right, so yesterday we talked about exponential growth. Today we're going to talk about exponential decay, which is essentially the opposite of exponential growth. What we need to know in order to kind of prep ourselves for some of the examples today is you might see the word half-life in these examples. And that basically means the time for something to be cut in half. So if you see the word half-life, it's actually telling you that your decay factor or your B value is a half. And that doesn't mean there's such thing as a full life. So just because it takes 2 years for something to half doesn't mean it's going to be gone in 4 years. It just means every 2 years the amount that you have is cut in half, and then the next 2 years it's cut in half again, and then after that it's cut in half again, and so on. When we talk about decreasing exponential functions or exponential decay, the graph of exponential decay is going to kind of be the opposite of the graph of growth. So let's just recap on what growth looked like yesterday. So when we were looking at some growth questions, we had something that was kind of starting small and then it gets really big really quickly. So that's kind of what growth is going to look like. Decay is almost like a horizontal reflection of your growth. So it's actually going to start big and then it's going to get really small really, really quickly. So just like so. Okay, we're going to do more work with graphs a little bit later in this unit, but for now this is kind of what you want to visualize as we're doing some of these questions. Can I scroll? Okay. All right, so I'm going to give you guys some examples of exponential decay. So the first one is nuclear power plants. They use uranium-239 as a power source. This uranium has a half-life, I'm going to underline that, that's important, of about 2 years. Ooh, 2 years, that's also important. Make a chart for the amount of a 1,000 milligram sample and how much is going to be left after 10 years. Okay, so when we think half-life, we want to think that our decay factor or our B value, guys that are talking right now, let's focus in here, okay? We want to think about our B value as if it's a half. Okay, so yesterday we did like some doubling and tripling questions and our B value was like 2 and 3. When you see half-life, you're thinking B is a half. Okay, so we're going to look at year 0 and then I'm going to go by 2s from here. So 2, 4, 6, oh, that was a 5, 6, 8, and then up to year 10. And then we'll take a look at the number of half-lives that have happened and the amount of our 1,000 milligram sample. So we're starting with 1,000 milligrams at year 0. And of course, at year 0, 0 half-lives have occurred, right? If no time has passed, then no half-lives have happened. Now, after 2 years, how many half-lives would have happened if a half-life happens every 2 years? Josh? 1 half-life happens after 2 years, and what does that mean about our 1,000 milligram sample? If it's being halved, how much is left? 500. Okay, so we're essentially multiplying by a half here, or dividing by 2, in other words. Okay, after 4 years, how many times has our sample been halved? Or how many half-lives have happened? 2. Because every 2 years, 1 half-life happens. And how much is left of our sample? Charlie? 250. You got it. Okay, so we're going to kind of continue with this pattern. Of course, after 6 years have happened, there are 3 half-lives that can fit in that time period. And our 250 milligram sample becomes a 125 milligram sample. Okay, and so on. So after 8 years, 4 half-lives have happened. After 10 years, 5 half-lives have happened. So we'll continue to cut in half here. So here we get, what, 62.5, and then 31.25 after 5 years. So technically, this sample is never ever going to really fully be gone, right? If I just keep halving and keep halving and keep halving, am I ever going to hit 0? No. I will get really, really, really small decimals eventually if I keep halving this and keep halving it and keep halving it, to the point where probably our instruments that we have for measuring these things, it would be undetectable, right? But really, this goes along with this idea of like matter can neither be created nor destroyed, right? So I don't actually ever get rid of all of this. There's still always going to be a little bit left, even if it continues to decay and continues to halve. All right, so just a recap on our equation from yesterday. We are going to use this equation for decay examples as well. It was y equals a times b to the x, where a was our initial value, and b was our growth or decay factor. Okay, for the x part of this, we remember that x usually has two components to it. What are the two components of x? So x here is actually the amount of half-lives that have occurred. So that's how our x is changing. I need to take my total time, which would be like 0, 2, 4, 6, 8, and so on. And I need to divide it by the half-life period, which is 2 years. So when we think about x in terms of our question here, x is going to be equal to total time over the half-life period. And we know that the half-life takes 2 years. So we'll call this t over 2 years. Now if I want to know how much remains after 25 years, then for my x value, I can just enter in 25 for the total time, and it will be 25 over 2. Now we're going to practice leaving this as a fraction because although 25 over 2 is just equal to a finite decimal, like it's just 12.5, if I had 25 over 3, let's say, that would actually be a decimal that repeats forever. And we'd like to enter in things as precisely as possible, especially in exponents, because the more I round an exponent, the further and further off my answer will become. So we're going to practice leaving this in fraction form when we enter it into our calculator. So here our initial sample was 1,000 milligrams. We were talking about a half-life. And we've entered in x as 25 over 2. Martez?
How do they find out what pi is?
What?
How do they find out what pi is? Like, how do they know it's 3.14?
I don't know, actually. Well, actually, okay, let me just pause this for a second so it's not. All right, now that we've gone on that little pi bunny trail, let's go back to this. We are going to make sure that we follow BEDMAS here. When you enter this into your calculator, make sure that when you hit your exponent button, you put 25 over 2 in brackets. Okay, so let's try this out. Do half to the exponent, 25 over 2. Get that answer and multiply it by 1,000. Again, I know 25 over 2 is 12.5, but let's see if we can enter this in as a fraction in our calculator, just for practice. And if necessary, we'll round to 3 decimal places here. What'd you get, Emma? 0.172. Anyone else get 0.172?
Are we calculating the whole thing or just the...
Whole thing, yep.
1.726334915 times 7 power -4.
Okay, so if it's 1.72, it's 0.1726, that will round up to 173. If we round to, was this grams or milligrams? Milligrams.
Kilo.
Okay, so 0.1726, the 6 rounds the 2 up to a 3. Final summary of this would be after 25 years. 0.173 milligrams of uranium-239 remains. All right, plutonium-239 has a half-life of 24 years. Find the amount of a 50 milligram sample after 35 years. Okay, Y, B, A, and X. Can somebody tell me one variable that they know from picking out information here?
I can't.
Sheila.
B is 1 over 2.
B is 1 over 2, and that's because we have a half-life. Very nice. What else do we know?
Is, no, I don't know.
That's right, we don't know why.
Yes.
Good job, Martez. What else?
That's all.
Do we know the initial amount?
24.
50 milligrams.
You know what's funny is 24.
And anything to do with time, so your half-life period and your total time, those will go into your X. So which one's the total time and which one's the half-life period here? Total time is 35, and the half-life period usually is listed right after you see half-life. We'll say like half-life of 24 years. That is our half-life period. Okay? And also, please note that these are both in years. If they were not both in years, I would want to switch the unit of measurement of one of them so that I can have them both in the same unit of measurement. Are you going to write any of this down, or do you have a pencil in your hand?
I just put it down.
Perfect. So pick it up. Let's get going.
I did write it down already.
Okay, perfect. We're writing more now. It's funny how that works, eh?
Yeah, it is.
All right, let's plug this into our formula. Okay, you will notice that if we do this as a decimal, it's actually a repeating decimal. It's 1.458333333, 35 over 24. So much better to enter this into our calculator as an actual fraction. The more you round along the way, the more your final answer will be off, especially with exponents. So try to enter this in as a fraction, okay? See what we get.
18.19.
18.19, anybody else? Okay.
18.195, so it'd be 18.
Yes, it would. Very nice. Or we can say 18.195.
Well, actually, the next number is 6, so it'd be 18.
All right, 18.196 it is. Here we go. Okay. Who wants to create our final statement for us here? George.
Would it be, after 35 years, there would be 18.1956 milligrams of plutonium?
Yep, perfect. After 35 years, there is 18.196 milligrams of plutonium-239 remaining. Beautiful.
So what happens? It just decays away into the atmosphere.
Yep. So you know, like, so a lot of these elements that we're talking about are like radioactive elements. So radioactive elements, they decay. They're kind of like unstable. So like, for instance, when you have an area where like a nuclear reactor has exploded or whatever, yeah, eventually those levels of radiation become safe levels of radiation and you can enter the area again, right? That's because those elements are slowly decaying over time.
I just
Okay, so the first couple examples that we did, we were working exclusively with half-life. But with exponential decay, you don't always have to be working with half-life. You could be working with just like decay factors that are between 0 and 1. We can also kind of flip what we talked about yesterday with growth by a percent. Charlie and Josh, focus in, okay? We can talk about what we were talking about with growth as a percent. in terms of decay. So we can be decreasing by a percentage value. So yesterday we talked about how growth by a percent, like if we have 8% growth, it's actually 108% growth because I have 100% of what I had before plus an extra 8%. Now if I'm decreasing by, let's say, 16% in this question, how much percent value actually remains? 84%. So when I go to calculate B, I'm actually going to take 100% and subtract the decay percent so that I know how much remains. So with growth, we add the percent to 100. With decay, we subtract the percent from 100. And here we're going to be left with 84%. And 84% as a decimal, 0.84, that's right. So that is going to be our B value for this question. Notice this is a value between 0 and 1. That's decay. If your value is greater than 1, Liam, turn around. If your value is greater than 1, that's growth. So 0, between 0 and 1, we know that this is actually going to be decreasing and it is a decay factor. Okay, so you buy a new car for $24,000, that's its present value or initial value. It's decreasing by 16% each year, which means 84% of its value remains. How much will the car be worth in 8 years? So when you go to calculate X here, our total time is 8 years. And it decreases by 16%. How often? Every 1 year. So it's like 8 over 1 here. And our question mark is, Martez, what don't we know? Yes. Very nice.
They didn't know that.
Exactly. All right, so we're going to plug this into our formula from above. And just calculate. So what do we get?
1387.
So this is money, so we are going to round to 2 decimal places. So therefore, after 8 years, the car will be worth $5,949.02. Okay, any questions on this one? Okay, so the takeaway here.
Cars are cheap after a long time.
True, actually. What I wanted to kind of focus in on is this. So if you have growth by a percent, you're adding to 100%. If you have decay by a percent, you're subtracting from 100% and then turn your percent into a decimal. And yes, cars are not a great investment. They do decrease in value quite quickly. Actually, this would almost be high for an 8-year-old car. Yeah, maybe not. It would be okay. Depends what kind of car. All right. An adult takes 400 milligrams of Advil. Each hour, the amount of Advil in the adult system decreases by about 29%. How much Advil will be left after 4 hours? Okay. What do we know? Or what do we not know? Sheila?
Well, I know B,
Okay.
if I'm right,
Mm-hmm.
71.
Wait, how do they release
0.71.
The apple.
Well, like, I was
What?
30%.
Do they sweat it
It-
out? 100%.
How do you release all the food that you put into your body and all the things that you drink?
Biology.
I have no idea.
Okay, so we get 71%. I'll tell you when you're older. You get 71%, and this becomes 0.71. Okay, what else do we know? Cameron. Very nice. 400 milligrams. Martez?
We don't know why.
Very nice. You're right. And X? 4, and this is each hour, so that's 1 hour, right? So this is 4 over 1, so basically just 4. Okay, let's enter into our formula here. Yeah. What'd you guys get?
101.646722.
Everyone else get that? Great. 101, let's say 3 decimals here, so 647 milligrams.
What? 6467.
Okay, so therefore, after 4 hours,
No.
101.647 milligrams of Advil remains in the adult system.
That doesn't make any sense.
Why?
Because then, like, it would just stay there forever.
So technically, when we talk about like things decaying, technically it never really does ever fully decay, but the amounts get like so small that they're basically like undetectable, right?
So I have Advil in my body right now.
Well, your body also releases like excess, like if you have more vitamins than you need or like anything excess, your body releases that, right? So, okay, and your blood is also like replenished as well, so your body produces, yeah, new blood. Okay, so you guys can imagine that calculations like this, especially like when you're in the field of pharmacy, are important. Why would something like this be important to know how quickly Advil decays within a typical adult system? George? Yeah, so like you'll see on the back of like Advil containers or bottles or whatever, it says you can take 2 capsules every 6 hours or 6 to 8 hours. They know that because they've done these tests and they know how quickly that particular substance decays within the human body.
Imagine it says on the bottle, it just gives us this question. The Advil decreases 2 hours. That's why it says helpful.
All right, so this blood sample, so someone takes this 400 milligram tablet, a blood sample is taken the same day. The amount of Advil in their system is found to be 25.83 milligrams. How many hours after the tablet was ingested was the blood sample taken? Okay, so we still have a 400 milligram tablet. What do we know about the B value from part A? It's 0.71, that's right. And what else do we know?
Not the Y value.
We do know the Y value, actually. What's the Y value? Josh? Yeah, so this is the future amount of Advil. And we do know that X was total time T over. And how often did this 71% or the 29%? It happened every hour, so it happened every 1 hour, right? So here, this is really just equal to T. But it's important to take note of what unit of measurement your decay factor is in. So the final time that we get out here is actually going to be in the same unit of measurement as the period, the decay period. So we're going to get out time in hours. Okay, so let's plug in what we know. Okay, so I see an unknown and an exponent. What should I be thinking about right now? Yes, I should be thinking about log. Log helps us isolate for an exponent. Okay, what's the rule before I do log though? What do I have to make sure I have? That's after log. Before log, what do we have to do before logging? What's that? We need to move the 400. Okay, and we'll do that by dividing it. I need the base and the exponent isolated on one side in order to do log. Okay, so you have an option here. You could leave this in fraction form. If you decide not to leave this in fraction form, you need to write out all the decimals, okay, no rounding. And if it's a repeating decimal, then you're leaving it in fraction form. Okay, this one is a finite decimal. It actually ends right here. So I can actually express that as a decimal value. Okay, guys, you need to stop, okay? Okay, so now we've divided out the 400. Again, if this is a repeating decimal, you keep it in fraction form, even though there's a decimal inside a fraction. All right, now we can log both sides. And we'll use power rule. We'll parachute this guy down in front, and he'll be a multiple now. Okay, before I go entering into my calculator here, let's just get t by itself. How do I get rid of this log of 0.71?
Inverse log minus.
We divide it. Yeah, it's being multiplied by t right now, so we'll just divide it out. Awesome. Okay, so we're going to enter in that expression on the left into our calculator, and we'll find time. Also, remember, guys, if your calculator opens up a bracket when you put log in, just make sure you close it up, just so that there's nothing else accidentally getting included in that log. So what did we get? Em, what'd you get? Did you enter it?
8.00001596.7.
Right. So I think we'd be safe to say about 8 hours, right? We'll say 8. There's 4 zeros after that, so I think we're okay. Okay, so therefore, who can make our final sentence for us here?
Therefore, our true value is
Or let's just say, so this question was asking us how many hours after the tablet was ingested was the blood sample taken. So George, what would you say?
The blood sample was taken 8 hours.
Yeah, that sounds good. Perfect. Any questions on this one, guys? I don't like that look. Stop looking like that. All right. He looks devious. I don't like it.